Good afternoon. So we are experts in GPS, and we're here to share with you a breakthrough in the GPS technology. GPS is, of course, this amazing invention where you use signals that are broadcast from satellites orbiting the Earth 20,000 kilometers away from us, and you're still able to compute a sub-meter accuracy position on the surface of the Earth. However, here comes the problem. As one of our car maker customers likes to put it, GPS tends to get highly temperamental in urban environments. So, have you guys ever experienced GPS misbehaving in cities? I have. Well, we have a truly differentiating solution for this problem. Good news, it's a software update to your GNSS sensors. And our talk today is, as was already presented, about enabling hands-free driving in dense urban environments. We're going to have two presenters, Dr. Ramsey Faragher, founder, president, and CTO of Focal Point Positioning. He's a well-known world expert in GNSS and positioning and navigation technologies and holds over 100 patents. And myself, Manuel del Castillo, and VP of Business Development at Focal Point with 20+ year experience in the GNSS industry. Let's start with our press release of this year. Focal Point has had a strategic investment from GM Ventures, and there's collaboration with General Motors on integration of next generation GPS technologies. What's this all about? It's all about integrating the software solution I was referring to previously in your existing GNSS sensors, so they don't misbehave in cities. This is our contribution to a more reliable and safe hands-free driving experience. So the goal for the OEMs is to expand the operational domain of autonomous driving and maximize the system uptime and safety. The challenge, however, for an ADAS system is that autonomous driving relies on GNSS, but as we said before, GNSS sensors misbehave in cities. And the target for the GNSS sensors is to maximize the availability of lane-level accuracy in all environments, including cities. So, in order to overcome the challenge, we can approach the problem like throwing more sensors to the problem, but with the, of course, limitation of extra hardware and costs, throwing more complexity at the problem with the limitation that complexity is always difficult to manage, or throwing services with ongoing costs. Our approach is very sensible, we think. We say, let's maximize first the utility of the existing sensors. And by doing this, you'll be able to solve the current pain points of GPS, which is lane identification in cities, lane identification in tertiary roads surrounded by forests or covered by foliage, lane identification in highways that could be surrounded by high cement walls, or lane identification even with suboptimal concealed antennas that are used to enhance the design of the vehicles. So this is representing the role of GNSS in an ADAS subsystem. Here's, of course, the perception subsystem. the planning subsystem, the control subsystem. The GPS sensor is part of the perception, of course, and responsible for absolute positioning. Absolute positioning is pretty unique. It can only be done by GPS, and it has a lot of critical functions, one of which is georeference, the HD maps, of course, lane identification, as was said before, in all environments, initializing and calibrating the relative sensors up there, so they locate you within the lane, and other features like geofences that could be used for roadwork awareness or stuff like that. So I think with this, I'm going to hand over to Dr. Ramsey Faragher that will go deeper on the sensor challenges.
Thank you, Manuel. I'm going to talk you through why it's such a challenge to get all of these sensors on our cars to play nicely together. What you want to do is to collect together a nice set of sensors that are all complementary and have different failure modes and can all work together to solve the overall problem of trying to replace us, the super intelligent species on this planet that is so good at driving cars. And there's two categories here in this table. The upper section are the relative positioning sensors, so things like cameras, lidars, and radars. They're brilliant at sensing the information in a short distance away from you in order to perform collision avoidance, just like we do with our eyes when we're driving. The stuff at the bottom is better at the sort of global navigation problem of trying to get you safely the 3 hours drive that you're doing and navigate to your destination. And things like lidars, radars, and cameras have a lot of computational load associated with them, and they're primarily good for that local position fixing. But you can combine them with HD maps to localize yourself in that big global frame. But then HD maps need to be updated. There's again a lot of complexity and cost associated with keeping them up to date, and it's not ideal to use these sensors that are perfect for short-range collision avoidance to solve the global navigation problem. It doesn't really scale. What does scale brilliantly is GNSS, these satellites that are orbiting the Earth, that we, by a $1 chip, put it inside our phones or our cars, and we can work out anywhere, we can work out wherever we are on the planet to within a few meters, and we can combine them with accelerometers and gyroscopes to get through tunnels and other issues. So on the face of it, it's all looking really good. It looks like this table is everything we need. But when I press the correct button, you get the error budget for a GPS receiver. And if you just pay attention to that error column, I'll talk you through all of the things we need to get rid of in order for GNSS to give us lane level accuracy. So you need to know stuff about what's on board the satellites.
You have the pointer also.
Yeah, thank you. You need to know stuff about what's actually on board the satellites, the electronics on there. You need to know where the satellites are in space as accurately as you can, much better than this number. And then you've got issues with the atmosphere. So the atmosphere delays the signals and causes errors. So this stuff here all has to get reduced to 0. And the good news is we can do that today by passing correction data over the mobile phone network to your cars. And so they're kind of solved problems now. You can just get data every few hours that get rid of these issues here. And that leaves this stuff at the bottom, multipath interference and non-line of sight signals. And as you can see, you can get up to dozens, hundreds of meters of error from those problems. Those problems don't really manifest at the top of a mountain or on a freeway. They manifest in city environments because they come about because GPS signals are at 1.5 gigahertz. The buildings we choose to live in are brilliant reflectors of 1.5 gigahertz. So we live in a hall of mirrors to GPS. If they were all really good at absorbing the signals, then we'd have much better positioning in our cars and cities, but none of your mobile phones would work. So it's a good thing in some senses that the signals bounce around so much for mobile phones, but not for GNSS. What we want is the kind of blue ones on this plot. We just want the line of sight signals. The maths inside the GPS receiver requires the signal to come in a straight line from the satellite to you to work out accurately where you are. when the signals do bounce off stuff, they've traveled too far. And one of two things can happen. If you haven't got the line of sight at all, and you only pick up the non-line of sight signal, then it literally pushes you away from the true position. If you're picking up both, if you're getting the line of sight signal and you're getting the reflected signal, that's like having a conversation in a really, really echoey chamber when your own voice is coming back to you and confusing the person listening to you with this overlapping conversation of what you're saying with lots of delays of what you're saying. And that corrupts the signal and again, moves you off the correct place on the map. And luckily, this is the thing that Focal Point has solved. So the software that Manuel referred to that we can put inside a GPS chip, for the first time allows the GPS receiver to measure angle of arrival. It's not possible to do this with any other technology but ours or a really expensive antenna array, which you do not want to have to mount across the roof of your car. But in software alone, we can steer beams of sensitivity towards the satellites. So we literally look in the right direction to pick up the signal, and we can detect when the signals are coming from the wrong direction and we just ignore them. So we clean up the multipath. If we go back to our table of errors now, those ones go away with correction data that comes over the cellular link, and all of these numbers reduce to 0 because of clever software inside the receiver. You can read all about it in some literature in the GPS community. It's called supercorrelation, and you can come and find us on the booth to get more information. The key things are that angle of arrival detection. Once you've got that capability, you've got a big sensitivity boost, a big accuracy boost, a big security and integrity boost. So we can detect and ignore spoofers, for example, which is when people try to broadcast fake GPS data to make your receiver think it is somewhere else. Great for cheating at Pokemon Go, for those who like that game still, but it's going to be a problem that is going to impact self-driving cars more and more over time. So supercorrelation is the name of the technology. When you put it into a GNSS receiver, we call that an SGNSS receiver, and SGNSS Auto is our offering specifically for the automotive sector. Here's some example results. This is just radio data, so there was no accelerometer and gyro helping out here, which is why the red line is quite so bad. This is in London in Canary Wharf. And so the red line is normal GPS processing, the blue line is SGNSS, which in all of those nasty urban canyons has basically detected when a signal has come from the wrong direction, got rid of it, and only kept the data that's coming in a line of sight, and has kept us on the straight and narrow. And you can see the errors get dramatically improved. So normal processing can end up with position errors out beyond 100 meters. SGNSS keeps a nice tight error bound on those solutions. So when you take this sort of level of performance and now add back in accelerometers and gyroscopes, then you get down to really accurate lane level positioning just from GNSS and inertial sensors. So there's lots of improvements across various metrics. This is the amalgamation of a bunch of results from half a dozen GPS chipset companies across the mobile phone sector and the automotive sector, over 100 different experiments over many years, 50 hours of trialing, and this is a kind of general view of the performance improvements. So a 10 times increase in sensitivity is the equivalent of taking one layer of brick and putting that on top of your car with the GNSS receiver underneath, and driving with a layer of brick on top of your car and getting exactly the same GPS performance. So it's a significant increase. We can literally see through buildings with this technology. Integrity is the score of how trustable the data from the GPS receiver is. And obviously, if you're only keeping the good data and throwing away the rubbish, then the trustability of the GPS fix goes up dramatically. That's very important for vehicles that have no human operator to be able to determine if they think the line on the map is not in the right place or not. The accuracy there is referring to both position and speed information, and the nastier the environment, the bigger the performance improvement we provide, as I just showed. So it can be up to 12 times better in positioning in urban environments. And I've already mentioned the cybersecurity angle of getting rid of spoofers. The sensitivity aspect is quite an interesting one because cars are actually getting nastier environments for GPS receivers. So adding more and more electronics into the cars, which increases the general aura of electromagnetic interference, and moving to electric vehicles makes this even worse because of all the switching and other aspects that are going on inside an electric vehicle. So cars are becoming little mobile jammers that are being taken along with the poor old GPS receiver. So the boost in sensitivity is very well timed for that. And there's also been interest in some entities to try and remove that shark fin antenna, hide the antennas in different places on the vehicle for aesthetics, and of course removing the antennas from the top of the car and placing them in other places and hiding them under parts of the bodywork obviously decreases the sensitivity of the antennas. So GNSS Auto pulls those issues back up out of the noise floor again. And I mentioned cybersecurity just before. It is a growing problem. There was a recent YouGov survey that captured the growing concern amongst consumers of cybersecurity aspects of driverless cars, including the aspects of GPS jamming and spoofing. So we're really pleased to be part of a solution to a problem that is still coming, but it will come. And I'll hand back to Manuel to round up. Thank you.
A few closing remarks. Safety and availability of ADAS is the focus of the industry these days. Innovative software upgrades to the existing sensors is the way to solve the pain points of GPS. Lane level identification in cities, as I said before, tertiary roads under foliage, highways with high tolls, cement tolls surrounding them, and concealed antennas. And finally, GNSS Auto is the software solution we have that enhances the utility of existing GNSS sensors. And we would encourage you to visit our booth, meet us in our booth for follow-up conversations on our technology. We have a booth right there, close to the gate. Thank you.